No.
Okay.
None whatsoever.
So we'll go slow, interrupt me, ask questions. We use a lot of jargon in electrochem, so if I say a word you don't understand, ask me what the word means. It's okay. Everybody, you know, like I at one point didn't know what the word electrochem meant either. So,
You think you do now?
So, over here is the full flow system that we have. So you have a tank that's full of electrolyte. It's the copper sulfate solution with sulfuric acid, right? And you'll see that it's piped into a pump down here. The pump is controlled by a valve. Okay, so real quick, if you're operating the valve, do use the face shield. I don't anticipate us having any big leaks. If we do, better safe than sorry, right? So if you'll bring your attention over this way, we have a flow meter here. That's a Keynes flow meter. The red number will give you your flow rate in liters per minute. Okay? It's piped into flow cell here. And I'll talk about the individual components now. So this back plate here, that is your anode. You're holding oxygen on your anode. Anode, by convention, is a positive reaction. Okay. You have brass plates. You're going to be plating the copper onto the brass plates. Okay. The way that you make a good seal with this flow cell, because you can see it's open-ended, is basically by pressing it onto this gasket. Oh. So everybody pay very close attention to how I'm setting it up. Right? I'm pressing everything into the cell backwards because by the fact that it's machined. Okay? So just understand that this is loose. And then anytime we're actually doing something wet, you know, if throughout the experiment we're going to be putting sulfuric acid solution into the cell area, I'm going to be throwing the rubber gloves on. It'll take a little bit. But, yeah, so anytime you're handling something that has sulfuric acid, make sure that you have chemically compatible gloves. So everybody's going to go through the process of putting the plate on because it might look really easy when I do it because I've done it 100 times. It's a little unintuitive how hard you need to press to actually get it to sit right. Pay very close attention to when you're sitting the seal, that you're relatively even north-south, and then you throw some pressure on here, you should hear it pop. Okay? Every single time, you want to hear it pop. If it doesn't pop, you're not actually sealed. The other thing, this might move a little bit if you're not holding it correctly, so have a teammate. I'm going to talk quickly about the electrode system. So, unfortunately, like I said, there's a lot of jargon in electrochemistry, and there's jargon between what the equipment is and what the science says, right? So, you have a cathode and an anode, which is much more conventional, probably something you learned in Chem 1 sort of thing. There's also ways to name things like counter electrode and working electrode, right? So what does that mean? The working electrode is the one the potentiostat software cares about. It's the one that you're giving instructions to, okay? So the counter electrode is just how do you balance the charge on the other side. So in this case, the counter electrode is the anode, the positive reaction. It's labeled red here, it's labeled red coming out of the potentiostat, and it's even labeled red on the cell itself. So red to red, right? Ideally, try and have it so that the label's sticking out. It's very important that I'm able to see what electrodes are connected where. A big nightmare is if we reverse the direction of the current that it's supposed to be, and then we get a bunch of copper on the anode plate. It'll probably stop the experiment for the day, and then we'll have to come back. Nobody wants to do that, right? So as I mentioned before, you have a working electrode that in this case is going to be your cathode. Okay, so it's labeled black by convention. It'll go directly to the brass plate. Okay, and we have one more electrode. It's our reference electrode. So the reference electrode in this case is a copper stub that's through the middle of the flow cell. And basically, the idea is, you know, the voltages are only really measured in differences. So it needs to be against some reference point, right? So what the potentiostat is really doing is taking one lead and it's actually shorting the working electrode. I didn't show you that, but I can show you if you're interested. And this is your other voltmeter lead, right? So it's basically just doing a voltmeter measurement while you're doing electrochemistry or using the voltmeter to tell the working electrode what to do. Okay? So this is for this first experiment. I'm going to clip to this copper sub back here. Very important to make sure that your electrodes are not shorted. Right. So if you have metal touching metal, you're going to throw off everything that goes on the software. It's going to give you nonsense results. You do not want that. So now that I have everything set up, real quick before I keep going, any questions?
Can we also measure the voltage of the anode relative to the reference electrode?
You will not measure it directly, you'll measure it indirectly and calculate it basically, but you will go through the process of gathering that data. I'll explain where you'll see, when I do the demonstration, and also do read through the 18-pager lab handout because there's a lot of information there, but it is all very useful for your pre-lab and everything else. So this door basically has a switch attached to it right here. Unless you hear that click, your switch is not engaged, so you will not get power to your pump. Okay? So the tricky aspect of this is I'm going to close it. You heard the magnet snap. Unless you hear that click, your pump's not going to run. Right? We also have an external switch that when you click it on, the power will actually start. In case of emergency, that is what you turn off. You turn that off, you leave the lamp. Right? Simple enough. One thing I will say is since we basically had to rebuild this thing from scratch, I'm still working out some of the small leaks, so when I start this up, it's going to leak a little bit. It will go away once the flow profile actually develops, so it shouldn't really affect the demonstration, but just now, it's going to leak a little bit out of that side probably. So down here, on the flow meter, I have it set to about 5 liters per minute. I've already done that ahead of time. But you see it takes quite a while to get there, so just be patient when you're taking those measurements. Don't start adjusting right away. Just give it some time to make sure it's actually settled at value. Right? So you can see now, that whole time I was talking, it finally just got to 5 liters per minute. Okay, so now we're flowing, we're pretty happy. I'm going to show you the potentiostat software and how you operate the cell basically. So this software is called CoreWare. It is what controls the experimental software that we use for data analysis. And I'll show you that too. But first off, if this screen isn't up, which I hope doesn't happen, but is a possibility, no need to worry. You can just start a new experiment by pressing this insert button. It's the one with the little caret next to it. And if you all want to come in closer so you can see everything that's going on, that's fine. So again, you'll see if you just drag over it, it'll say insert. And if you're not sure where something is, just drag over it. There's setup. We're not going to deal with that. But we're not dealing with that. We will do measure selected at one point. But just understand that, if an experiment is missing, you insert, you'll see the full experimental list. The two that we're going to use for this lab are potentiodynamic. That means you're changing potential with time. And then galvanostatic, which means you're applying a constant current. Okay, those are the only two we should need for any of this, but just so you're aware. So the first demonstration we're doing is the polarization curve on a 3-electrode system. So if you look over at the cell, you can see that there are 3 separate electrode leads going to that cell, right? That's the 3-electrode measurement. Briefly, before I move on, you will see an open circuit potential readout. When you're against copper and copper, or copper and brass, which is largely copper, you'll see that the potential difference isn't very large. It's 30, 50 millivolts, something like that. When we go to switch the electrodes later, it'll be much different, and I can kind of explain why and why that matters. First things first, you should go into your files, so hit the folder button. Demo day afternoon, that's not us, right? So we're going to go to the ECHG 362 folder. We can do demo day morning. So you can see that there's all the morning session files from the other day. And what are you, group B? B? Okay. So we're just going to go group B. And today's the 4th, I think. And this first measurement is going to be 5 liters per minute, and we're going to go against the reference electrode, so just so we're aware. Label it properly. make sure that you have all the information that you need to easily understand what the file is. I know that sounds simple, but it'll save you a lot of headaches. So once we've saved it and given it a unique name, we can actually run the experiment when it comes down to it. So you'll notice I do not have any of the use things checked. What that'll basically do is if you were to do that, it would sweep backwards. It's a waste of time, it's a waste of electrolyte. We don't need it for this experiment, so we're not going to engage with it, right? Generally speaking, always start 0 volts versus open circuit, so it's going to give you 0 against that number, which means it won't be passing any current at the 0 point, which is kind of what we want. And for the 3 electrode measurement, do it against the reference electrode. And we're going to go to about minus 0.75 for this. The scan rate is 20 millivolts per second in this case. It's just, we need enough time for the boundary layer to actually develop and get to that limiting current value. Okay. So, satisfied with all of this. Before I measure anything, do we have questions? And also, feel free to just interrupt me. I realize I just talk a lot, but yeah.
You said 0.75 volts is all it takes to get to limiting current?
Yeah, against the reference electrode, yes. So it's going to change when you're doing a full cell measurement. Yeah, you'll see it later. I'll show you.
Okay.
Yeah, so this should take, I don't know, 30-ish seconds. 35 seconds maybe. But you'll be able to see, like I said, we're going to start basically at 0 current. And if I've done everything correct, this should end up limiting out around minus point, I don't know, 65-ish. Let's see how I did. All right, minus 0.66, so pretty close. It'll tell you that your measurement's finished. If you want to look at that data, you open this program called CView. It should also pretty much be open. If it's not always open, I'm sure there's a desktop shortcut right here, okay? So if you want to look at a data file, you hit the C folder. Again, we're not in demo day afternoon, so if you need to go back, just directly one folder, you hit that one. Now you're in the senior lab folder. You go demo day morning. Organized by date, you can either double click it or scan over it and hit the right button, whatever works for you. And you can see that we have our data from the experiment we just did. Now if you want to zoom in on it, you basically just drag a box over it, right? And then if you don't like where your zoom is, if you want to auto zoom, you hit Control A. And that'll change the ratio for you. So that's going to be more important when we have the other experiment up next to it, which we'll go to right now. Any questions before I move on? Yeah.
Why is there a different limiting current for each of the electrodes?
Each of the electrodes?
You said that there was a limiting current for the reference, and then there's a limiting current for the others?
So the way that you perform the measurement, you will have to change the parameters that you put in. So it's just, the limiting current should not be different. Functionally, that's like the electrochemistry should be the same, but what you tell the instrument has to be different depending on the way you make the measurement, right? So if your reference electrode or your voltmeter is sticking like on the working electrode and the reference electrode, it's only going to give you that measurement or get instructions based on those measurements, right? If you have it set versus the counter electrode or an open circuit type measurement, it'll only give you that value against the counter electrode, right? So those voltages are going to be different. Therefore, the instructions are going to be a little bit different. Does that make sense?
A little bit.
Yeah, yeah.
Kind of.
Yeah, just mull it over, and if you have questions, like, just hit me. All right, so now that we're done that, we need to adjust where the electrodes go, because, again, we have 2 polarization measurements. There's the polarization versus the reference, and the polarization versus the anode, or in this case, counter electrode. So again, do not handle the sulfuric acid solution without these gloves on, or come near it, really. So again, all I'm going to do, take the reference electrode, and I'm going to move it to the anode state. Okay? Make sure you hear the click. Actually, just to make a point, hold on. It does run. So now, second type of polarization measurement. So again, we're going to head back into CoreWare. Once again, open the potentiodynamic setting or experimental setting. You can also change the file right from this little pop-out. It'll carry it over, so I'm going to put versus counter electrode here. And you can see that when I hit the folder, it actually carries over. Okay, so what am I going to do differently? I'm going to specifically make all the measurements versus open circuit, and going to add a small amount to the sweep to compensate for the extra ohmic resistance that we're facing. So you'll notice if you pop in here, you have about an additional volt of open circuit voltage, right? So if when you're saying versus open circuit is 0 versus that number, so starting at that number and then sweeping to the next one. Okay? I'm pretty happy with all that. So let's hit OK, and measure selected. And it's really important also, do check your flow rates as you're going, because that will have a pretty large impact on how the experiment performs. In this case, we're sitting nicely at 5. Again, you need to adjust it. Please use the phase shield. So you were asking me about voltage differences, right?
Yes.
So again, we're against the counter electrode in this case, so you'll notice we're not really at 0.75, right? We're starting at minus 1.05, and we're adding another 800 millivolts or so as we sweep this way, so it should end around, I don't know, minus 1.85, something like that. And we are fairly close to the limiting value. Again, if you don't quite get there, you might need to add a little bit more of that sweep just to make sure that you're driving it to the limiting value. Right, so in this case, we probably could have gone a little bit farther. You can see, when we open C-View, we want to overlay these plots together. So again, I'll say, yes, we want to look at the sweep versus the counter electrode. Add that in. We don't see it right away because we're already zoomed in on something else. Just hit Control. And then you'll be able to see it. And again, like I mentioned, this one really didn't level out. We needed to give it a little bit more in order to actually see that limiting value. But just understand that when you're changing where that reference lead is, you're going to vary the amount of ohmic losses that you have in your cell, right? Because you're changing the distance between those two things. So,
it's only by 1/20th of a volt, the ohmic resistance that changes.
So the ohmic resistance will have units of ohms, right?
Yeah.
Yeah, so
Oh no,
I'm not sure I understand the question.
Wait. Oh, never mind. Okay. I'm
Yeah, so
confused.
if you look at some of the in the lab file that has all of the equations that you use, you'll see that there's a length value in your ohmic resistance equation.
Mm-hmm.
And since we moved the length of this electrode quite a bit, you're going to have some additional ohmic resistance when you make that measurement.
Did we effectively double the length?
Close?
Close.
Yeah, I wouldn't say it's exactly double, because I think that stub sits a little high. It's probably a close approximation though.
Can we use double for the lab when calculating it? Or?
So I think you should look through the note, because I think it tells you exactly how to go through that process.
Okay. All right.
Yeah.
You also mentioned, or the lab mentioned something about a reference being like negative 0.25 and then another number. What is that about?
Yeah, so this is during the pre-plating, so we didn't go through the whole pre-plating process here, but basically you're going to put down an amount of copper ahead of time so that you're measuring copper deposition against a copper reference electrode, so it's the same electrode basically. So when you're actually doing that copper deposition, your voltmeter should read about minus 0.25 versus the reference electrode during that very specific portion.
Okay.
It's going to vary depending on the type of experiment you're running.
Will we enter with copper already plated onto our brass plate?
You will have to do that yourself.
We'll do that.
Yeah, so, and this is a good point because the thing is I'm encouraging all groups to make sure that they clean their plates because otherwise I or they will have to do it in the beginning of the lab because you don't know how much copper has been plated down, you don't know what that surface morphology is, you don't know anything about that, right?
Okay.
It's just whatever that group gave you. So you want to make sure that you're dealing with a relatively clean brass plate ahead of time. And if you see stuff like this, it's, or that's probably a better example. You take one of these abrasive pads or some sandpaper and take it over to the trash and just abrade it so that you get a clean surface. Okay, same deal with any of them. You should always make sure that you have a clean surface. And in addition to that, after you abrade it, rinse it off, right? You don't want any residual dust floating around, specifically in that pump fluid system, right?
How do we know if the cupric ion concentration changes while plating?
It has to, right?
It has to, yeah.
Yeah.
Like by a negligible amount or a non-negligible?
You can calculate that.
You can calculate that. Okay.
Yes, in fact, you must calculate that.
We must. That makes sense. All
So,
right.
an important question, right? A part of your Excel that you should hand me for your pre-lab should include a calculation of how much of the cupric ion that you actually consume, so that I can make sure that the concentration is appropriate for the next group. Okay? Does that make sense?
What? Can you say that again?
Yeah, sure. So the Excel that you bring with your pre-lab
Yeah.
should have a calculation of how much cupric ion you consumed during your experiments.
In relative like Faraday efficiency or like?
Just assume, using Faraday's law, yeah.
Okay.
So assume a Faraday efficiency of 1, perfect efficiency, and then calculate it from there.
But it's not that, right?
It's probably pretty close.
It's probably pretty close. Okay.
Yeah. Faraday efficiency is tough to get perfectly correct, right?
Okay.
So like, good talking point, right? So you have a scale here, right?
Yeah.
You have a plate. This plate weighs 244 grams, or thereabouts, right? So 244.52, right? So you get second decimal precision. How much copper is a reasonable amount to plate? That's something that you really need to consider, because do you trust 0.1 when it just floated another 0.02?
Probably
not, right? So make sure that you're convinced by how much copper you're plating. Like when you're designing experiments, plate enough copper where you're like, you can trust that measurement, right? Because otherwise your Faraday efficiency could end up very different than what it really is, right?
So like a couple grams?
Not a couple grams. Okay. Think like tenths of.
Tenths? Okay.
Yeah. In the interest of time, I'm going to start the copper plating aspect of this. And if you have additional questions, you can just hit me as we're talking, so we're going to have about 5 minutes to wait here. So I'm going to hit this Galvano static setting, or experimental setting. Again, give it a unique name. Right, so I'm going to fly through this relatively quickly. Group B, this is the 4th. And again, I'm just going to kind of run this relatively quickly so that we can get to the rest of all of this. So, begin the experiment. This is probably going to be a pretty high cell voltage, like 2.1-ish. Yeah. And this is just going to run for the next few minutes or so. Yeah, now is a good time for additional questions. I'll make note that, if you have a wetted plate, a paper towel is not sufficient to dry it. So you have this heat gun here. take this over to the sink, right? Use the leather gloves, please. Do not burn yourself. Yeah, please do not do that.
Were we supposed to weigh the plate before we plated?
Yes, you are. I am not taking data for you right now, right?
Okay, yeah, probably.
So, yes, you should absolutely do that. Now, if I were, and the other thing is, this is probably not enough time for me to make a convinced gravimetric measurement, right? Like it's very borderline close on how much copper I'm putting down. So I wouldn't, this is just for demonstration purposes.
Okay.
And to help you be able to use the equipment.
How long is that?
So I'm probably going to stop this one after about 3 minutes, so I can show you how to shut down an experiment if you, let's say you made a mistake somewhere, right? We do make mistakes and we should be able to correct that or stop things before they get irreversibly bad.
Is the voltage going down because the ohmic resistance is going down?
That's part of it, yeah. There's some additional things that can also be affected by the deposition of copper that, take a look in the lab handout, and I think you can, yeah, you're going to have to read, sorry.
I read like 4 times, you don't understand.
Yeah, it's going to take a while. I mean, this is something that is not a part of the undergrad curriculum. Like we don't learn a lot of electrochemistry up until this point, right? So it's gonna be hard. It's gonna be a little confusing at first, right?
Okay.
Like it's easy for me because I've been doing it for 4 years now.
Okay.
Right.
Yeah.
All right. So in about 10 seconds, I'll give this a stop, and we can take a look at what the copper was plated. Okay, so this big stop sign up here, you hit. It'll ask you, do you want to name the file that, or do you want to name it something else because you've stopped it ahead of time. Hopefully, we don't have to do this at all, but... So, okay, you stopped. Shut your pump off. Take your gloves. Again, we just flowed a bunch of acidic copper sulfate over this place, so don't touch it.
Do you know how we're supposed to
I think
calculate the concentration?
it'll be funny looking back at this video because I'm so bad at getting the gloves on.
Sorry. How do we know the starting concentration?
Okay.
Okay.
Pull up your working electrode. Again, hold this in place so that you are putting pressure backwards. It'll take a decent amount of force. Unclip it all. Now be very careful with this part. It may be a little bit stuck from just being pressed up against the gasket for a while. So just lightly apply pressure, peel it off. You see we put some copper.
Those actually pretty fast.
So,
okay. So
give it a quick rinse. Just a little easier to handle. Collect it. Switch, well, ideally you have somebody else handling the copper plates after the fact, so you don't have to switch gloves badly during a demonstration. There are 2 settings on the heat gun, one of them is high, one of them is low. Just use the high setting, which is all the way down. Just a reminder, copper is very thermally conductive. So if you have it against something that can act as a heat sink, it'll probably try and give up that heat pretty readily. But you can see it dries off relatively quickly. really want that bulk water to come off, if you have a Faraday efficiency greater than 1, you did not dry it enough. Or if you did something else crazy. So, probably a miscalculation. And the last bit might be a little bit stubborn. See if we can't get that last little bit off. Okay, that's looking pretty good. Now, go through the process of weighing it. It'll increase by, whatever amount you put it on there times the Faraday efficiency. Again, that's what you're calculating. And please, doing experiments, please remove the copper. It is a little bit labor intensive, but it comes off relatively readily with an abrasive pad, as you can see. Okay.
At what point is it clean?
It's like a philosophical discussion at this point. I would say if it looks pretty much like brass or copper, you're okay.
Okay.
Yeah. If you see, again, a bunch of gunk, I wouldn't call that clean. But if you see something metallic, probably fine. Okay. So I think with that, we should take the time to just everybody practice putting the plate in place. I think I managed to skip through that. So